Welcome back to The Explainer. Today, we're jumping right into part one of our two-part look at building the model for ideal versus practical equivalent circuits. If you've spent any time at all studying electrical machinery, you already know there's this massive, glaring conflict between the pristine, perfect textbook theory of a transformer and the messy, heat-generating physics of real-world machines. So we're going to build the practical model totally from scratch, component by component. Let's see exactly how engineering bridges that gap between theoretical fantasy and physical reality.
Let's start with a quick reality check. An ideal transformer, it's basically just a fantasy. It assumes perfect magnetic coupling, absolutely zero power losses, and no electrical resistance in the wires whatsoever. But real transformers, they earn every single one of their imperfections. And while well-designed power transformers can get incredibly close to that ideal, they never actually achieve it. So to create a true, working mathematical model of a real transformer, we have to account for its flaws. We essentially have to bolt 4 major physical imperfections onto our ideal model, one by one.
All right, first up, we have our series imperfections. Step 1, winding resistance. Look, copper just isn't a superconductor, right? So as current flows through the primary and secondary windings, you're going to get resistive heating. Step 2 is leakage reactance. In the real world, some of that magnetic flux just escapes out into the air. And since air is a terrible path for magnetism, it has high reluctance, kind of acting like a massive roadblock, this escaped flux acts just like a self-inductance, sitting right in series with the coils. These two series elements, the copper resistance and the leaked flux, they are the exact reason a transformer's output voltage physically sags when you put it under a heavy load. Now, let's look at the core itself with the parallel defects, which we often call the excitation branch. These sit right across the primary voltage source. First, we've got RC, the core loss resistance. Think of this as the real power permanently burned up in the steel core. That's due to hysteresis, which is basically just the friction of magnetic domains flipping back and forth, and eddy currents swirling around in the metal. Right next to it is XM, the magnetizing reactance. This represents the actual effort, the reactive current needed just to set up the magnetic flux in the core in the first place. So the really crucial takeaway here, RC is the heat, and XM is the magnetic heavy lifting. Okay, let's pause for a quick puzzle. Imagine a transformer's secondary is totally open-circuited. There is absolutely nothing connected to the output. Yet, if you put an ammeter on the primary side, it still draws a small current from the source. Why would a transformer draw power if it isn't supplying any power to a load? Take a second to apply what we literally just learned about the core. Have your answer? Well, here's the reveal. That no-load current is completely real, and it is absolutely not a fault. RC and XM, the core losses and the magnetizing current, they honestly do not care whether a load is connected to the other side or not. Because they sit in parallel right across the primary, they are always on the clock. As long as there's voltage applied to the primary, XM is drawing current to magnetize the core, and RC is drawing current to overcome the hysteresis and eddy current losses. They're doing their job no matter what is happening over on the secondary winding. So, putting it all together, we finally get the complete, practical T-equivalent circuit. Notice how the ideal transformer is perfectly insulated right there in the center, flanked by our 4 imperfections to form a T-shape. Over on the primary side, we have our series winding resistance and leakage reactance. Then, branching off in parallel, we have our excitation branch. And finally, on the secondary side, we have the secondary series resistance and reactance. A really key detail here, the elements forming the excitation branch are placed inside the primary series elements, and that's because the voltage actually applied to the core is the input voltage minus the internal voltage drops of that primary winding. But we've hit a massive roadblock. While this physical model is highly accurate, it is absolutely terrible for math. As our source material points out, to actually analyze practical circuits, we have to convert everything to an equivalent circuit at a single voltage level. Trying to calculate a system that mathematically jumps from, say, 480 volts down to 120 volts right in the middle, yeah, that's an engineering nightmare. We really need a mathematical trick to get rid of that ideal transformer barrier right in the center. Enter the brilliant engineering trick of impedance shifting. Notice how that ideal transformer barrier is completely gone now. We've literally slid the secondary elements right over to the primary side. But you can't just move things for free, there's an exchange rate. To legally move an impedance across that barrier, we have to multiply it by the turns ratio squared. Think of it kind of like converting currencies. You have to adjust the value based on the exchange rate to keep the transaction perfectly balanced. This scales the impedances so that, from the perspective of the primary power source, the circuit behaves exactly the same. But the magic is, now it's just one single continuous, solvable line at a single voltage level. We've built the perfect theoretical map, we've bolted on the real-world defects, and we've learned the incredibly handy secret of impedance shifting. But here is the real puzzle to leave you with. How do you safely test a 10,000-pound piece of solid metal to find these exact, invisible, mathematical values without accidentally blowing the whole thing up? Well, we're going to tackle open and short circuit testing in part 2 of this explainer. Until then, keep asking questions.